Most.
So here's the first one. I think it's on problem number 1 on the most recent assignment right there. You're going to end up having to solve this equation. I think you're going to find, I think everybody's there, that the intermediate value theorem does apply. You meet criteria, right? And so now it wants you to find the values of the function where it equals 0, right? Okay, so we got to solve that equation. So for this one, I'm going to give you permission to legally cheat and just use technology to do that. Does everybody know how to do that with technology? Really easily.
Plug in the 0 and 1.
Well, no, but if we want to solve the equation, we're solving the equation 2x cubed plus x minus 1 equals 0. How would you use technology to do that? Yeah, graph it, and we could just Desmos probably, right? You can use your graphing calculator also, but if you graph this on Desmos, I'm sure everybody's got this, but let's just make sure. If I graph this thing on Desmos, if I graph f of x equals 2x cubed plus x minus 1. I want to show you a couple things here. So we're really only interested between 0 and 1 too, aren't we? In this case, right? It's on that interval. So we can do a couple things that are very helpful. We can go down to the graph settings, and we can let the x values run from 0 to 1, first of all. That's helpful. And then while we're at it, we might as well let the y setting. I mean, we don't really need to worry about the y settings. So if I click on the function then, between 0 and 1, when you click on the function, Desmos tries to give you important points on the function. It highlights them lightly in gray. So one important place is the x-intercept, right, which is what we're looking for, isn't it? We're trying to find the 0. We want to know where the function is equal to 0, right? And I'm not telling you anything you don't know. So there it is, right? There's your answer, and then it wants you to round it to some number of places, which you can do, okay? So it's easy to use technology. That's the way we do this in the real world most of the time. What if we're not wanting to use technology, though? I don't expect you to do it this way, but I want you to be thinking along these lines. What would our approach be to this one if we had to go back to like algebra 2? How could we solve that equation? Remember, this has been a long time ago. Okay, this is not a great method in a way, because if we'd use the rational root theorem, right? Does that ring a bell? Yeah. Rational root theorem. So the rational root theorem, what that tells you is that if you have some, and this is worth probably taking a second and reviewing, because this is pretty important item in math. So if you have a polynomial, if you have something like ax squared plus bx, or make it ax cubed plus bx squared plus cx plus d, for example, equals 0, right? What the rational root theorem says, if this is a polynomial equation like this, and it's in standard form, what it tells us is that all of the rational roots, any possible rational root, if it has rational roots, they will be, at least one of them is going to fall in this pattern. It tells us that the rational roots are always going to equal the positive and negative factors of the constant, so in this case d, divided by the positive and negative factors of what? Of a, right? So they're always going to be built from factors of the constant divided by factors of the leading coefficient, right? So all we would do in a situation like this then is we'd make a quick list of possible candidates, and we'd start with the easy ones and work our way down. So I don't know if I'm going to finish this today, but I'm going to show you something really cool that I probably didn't ever learn. This is a great way to organize your thinking on this. So what are the possible candidates then? Well, what's our constant? -1. Okay, so the factors of -1 are just plus and minus 1. What's our leading coefficient? 2. Factors of 2 are just 1 and 2, right? Yeah. The integer factors, what we're looking for. So our possible rational roots would be plus or minus 1 and plus or minus 1/2, and that's it, right? Okay, so a couple things then. How would we check these really quickly? How would we check to see if they work, if they are zeros?
So, plug it in.
Plug them in, but a really quick way to do that would be what?
Synthetic.
I mean, you said, yeah, we would use synthetic division, really synthetic substitution. If you want to check these very quickly, all you got to do, especially if you have big, ugly polynomials, the easiest way to do it is using synthetic division or synthetic substitution, right? So here's how we could set that up then. We'd have something like, you can use tabular synthetic division, which is a great way to do this. You don't have to do the whole thing. All you're going to do is you're going to write out what are the coefficients that we would use for our synthetic process here.
2, 0, 1.
Everybody agree?
Yeah.
Okay. And then we're just going to make a list of possible candidates, and they're either going to work or they're not. And this is going to be the column where if it works, we're going to get a 0 in this column, right? And then rather than writing out the whole bracket, we're only going to write the numbers that would appear in front of the bracket or underneath the bracket. So we'll do the first example the long way, and then we'll show you what it looks like when we use the tabular method. So this first column out here is just going to be the values that we're checking. Okay, so if we check, for example, let's check one that doesn't work, like 1/2. How about? Oh, what, 1/2? If you guys, did you learn how to do synthetic division with fractions?
Isn't it?
It's, well, it's almost the same. It's,
I know we did. Yeah.
okay, maybe, I'm gonna run out of time. Maybe I'll do that tomorrow. Okay, we'll take a quick moment and do that tomorrow. Let's find one that, which one doesn't work here? Let's see. It's gonna be, oh, the ones don't work, do they? Oh, yeah, they do. So, -1. +1. Do any of the ones work? If I put in 1, I'm gonna get 2. They don't work, do they? So let's show that they don't work. But let's try +1. Like if I plug in 1 synthetically, this is how we would write it, correct? We'd write it like, normally you'd write it like this. We're gonna try the 0, 1. Our coefficients are 2, 0, 1, -1, and we put our remainder box underneath the last coefficient. Awesome. And then we would just drop down, right? You tell me, what do I do?
2.
Drop down to 2. 2 times 1 is 2. Add or subtract synthetically? Add. Opposite of long division, right? Synthetic division is the opposite. We add. So we get 2, 2. So there's a remainder, right? So that one didn't work. Well, how would this look if we use the tabular integration, tabular synthetic division? We'd put the 1 out front. We drop the 2 down. 2 times 1 is 2 plus 0 is 2. 2 times 1 is 2 plus 1 is 3. 1 times 3 is 3 plus -1 is -2. Right? And that's a loser.
That's positive.
Positive 2. You're right. Positive 2. And so we would cross off then. We'd cross off the positive. And we'd move on and try the negative. And we just go to a new row. And you might even just want to put an X through that one so you know it didn't work. We drop down and try -1. Okay. Bring down the 2. 2 times -1 is -2 plus 0 is -2. -1 times -2 is 2 plus 1 is 3. -3 plus -1 is -4. So the negative crosses off, and we just move down the list. See how that works?
Yes.
Okay. Okay, how do you do, I guess we have time, how do you deal with the fractional ones? Because this is really helpful. So what if we want to try negative, or let's say positive 1/2 in this guy? Okay. What do I do? I mean, I can go through the same.
Do you just multiply all the factors by 2?
Okay, so there's a couple ways we can look at this. If I'm trying 1/2, then what I'm really doing is I'm trying to see if this function divided by x minus 1/2 gives me 0 remainder. Everybody get that? Okay, so let's just kind of move down here for a second. So we're just checking, does my original numerator, my original polynomial, 2x cubed plus x minus 1, divided by, we'll try positive 1/2. Well, if positive 1/2 is the 0, then what's the factor that goes with that? X minus 1/2, right?
Yeah.
Is this ringing a bell? You guys making that connection? If we're attempting x equals 1/2, then the factor on the bottom that goes with that is x minus 1/2. We're asking the 0 of what is 1/2? Well, x minus 1/2, right? Okay, that's kind of ugly though. What's wrong with that picture? That's a pretty ugly looking fraction. What would we do there to simplify that? I mean, we don't want to have a fraction, we don't want to have a complex fraction. We don't want to have a fraction within a fraction, right?
Yeah.
So what could I do to both the top and the bottom to get rid of the 1/2?
Multiply by 2.
You could multiply by 2, couldn't you? Right? So we could multiply through by 2, and that's going to give us, if I multiply through by 2, what's that give us? Well, that's going to give us 4x cubed plus 2x minus 1, right? And on the bottom, we're just going to get 2x minus 1. That looks better, but that violates our rules for synthetic division, because what's our rule for synthetic division? We have to have on the bottom, we have to be able to write this as a solution of the bottom. And so this is the point I want to make here, and I'm running out of time. Oh, dang it. Just pick it up tomorrow. We'll pick it up tomorrow.